So here we're asked to determine the equation of the graph. Just note that there is no vertical stretch occurred here or applied to this graph. Now, in order to determine this, we have to understand that this is a tan function. We can tell because there's asymptotes, and it's important to just understand what the regular tan function looks like. So in order to start graphing this, I'm going to talk a little bit about what our function y equals tan of x looks like, just the base function. Okay, so let's draw roughly what this is going to look like. Now, some things to understand is this can be represented as y equals sine x over cos x. And cos x cannot equal 0. So that's an asymptote there. Anytime a value of x in there causes this to equal 0, that's an asymptote because it's also a non-permissible value. Now, this is a repeating non-permissible value. If we think about our unit circle here, x is 0 at pi over 2 and 3 pi over 2, and this repeats. So pi over 2 here, 3 pi over 2 if we go more around, that's 5 pi over 2, then we go around even further, that's 7 pi over 2, so on and so forth. So this cannot equal pi over 2 plus x cannot equal pi over 2 plus n pi, where n is any real integer, okay? Because you're repeating every 180 degrees from pi over 2. So that means we have asymptotes here we can graph. So this would be negative pi over 2, this would be negative 3 pi over 2, this would be pi over 2, and then 3 pi over 2. So we can draw some dotted lines to represent those guys. And then from there, tan's actually pretty easy to graph because at this point here, this is a function of, when your angle equals 0, or let's say 2 pi or 360 degrees or whatever, your x value is 1 and your y value is 0. So for tan, that would be 0 over 1, because remember your y value is sine x and your cos value is cos x, or so your x value is cos x. So 0 over 1 equals 0. So that means at 0, 0, we have a point here, and this can also repeat. And what your graph's going to do is it's going to approach those asymptotes like this. There's more videos going more in depth on going over the tan function. I just wanted to really quickly refresh about it before we tackle this next question. Okay, and these repeat. This would be negative pi here. This would be pi. Our next value would be 2 pi, so on and so forth. So that's what our graph roughly looks like. Now, why am I mentioning all this? Well, because if we have a new function such as this, we can think about it as if we got this function by applying transformations to our y equals tan x. So if we look here, these are known as inflection points. Okay, inflection points are essentially where the graph goes from kind of a decreasing concavity, that's what it's called, to an increasing concavity. You don't quite have to understand what that means. You just have to understand these are inflection points. Okay, so we can see that it's kind of a change in direction. We're going, and then we're starting to point up. Okay, so those are inflection points. They can tell you where your midline is found. Okay, and your midline is going to be the value of k. So when we have a function that has been transformed, we can see it as y equals a tan b x minus h plus k. This is your midline here. In this equation, or in this graph, they tell us we have no vertical stretch, so this simply equals 1 for right now, so we're not going to worry about that in this example. How about b? What is that tied to? That's the that's the horizontal stretch. Now the horizontal stretch is related to the period. Now if we look here, the period of y equals tan x would be pi, okay? Let's say from this inflection point to the next inflection point takes pi units. To go from this asymptote to this asymptote takes pi units, so on and so forth. So t equals pi, and t being period. Now, b and t are related by an equation, and the equation is very simple. b equals pi over t when you're talking about tan. So we can figure out the inverse of the horizontal stretch by understanding what the period is in our new function. And then lastly, our phase shift, that can be determined in lots of different ways. But the main way is I always think about this midpoint, this origin inflection point. And then I imagine this thing being moved to different spots. And I think about, okay, well, how far did it go in the x direction? And that will be your phase shift. And we'll look at that. So let's start off here. The easiest thing usually to determine is the midline. Okay, so where are all the inflection points occurring here? Sometimes it can be kind of hard to see, but in this case, it's not super difficult. We can see that we're going in a certain direction, and then we change direction here. Okay, so we have inflection points here, 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 everywhere I'm drawing a black dot. Okay, that means we have our midline found there. So we can draw a midline roughly on the y equals -2 line. So our midline, we've already found that our vertical translation was -2 units down. We move that midline 2 units down. So k equals -2. So if we start writing this equation, we can already write that we went 2 units down. Okay. Now, how about finding the inverse of the horizontal stretch? So b. So b is related to period. Remember, in order to find b, we need to do pi divided by t, which is the period. How do I find the period? Well, let's think about either how far repeating asymptotes are or how far repeating new inflection points are. The easiest I can see here is this asymptote and this asymptote. And the reason I think those are the easiest to look at is because you're dealing with 0 to pi over 2. So you automatically already know that's pi over 2 units. Okay, so that would be t. Let's say we didn't have a really nice origin value, something not easy to work with. We could also think about our new inflection points here. Okay, if we look at our inflection points, let's say we wanted to use this from pi over 4 to 3 pi over 2. What's the distance between here and here? Well, on a number line, you can subtract to find the distance. So 3 pi over 4 minus pi over 4 gives us 2 pi over 4. You have common denominators, you have like terms. 3 minus 1 is 2, so 2 pi over 4, and this can be brought down and simplified into pi over 2. 2 divided by 4 gives us pi over 2. So your period, you could also find that way. T equals pi over 4, just like we found above here. So now we have t equals pi over 4, so we can solve for b. So b equals pi divided by pi over 2. Now when you're dividing a fraction, you can multiply by the reciprocal. So I'm going to flip it and multiply by pi. So pi times 2 over pi. Our pi's cancel, and we get b equals 2. So now we already have this value, which is 2. And the last thing to do is determine our phase shift. So again, lots of different points we could choose from. The easiest point is to think about, where did this inflection point, where does that midline origin inflection point go? Where did that end up? Well, remember, we have lots of inflection points to choose from. we could use our phase shift based off this inflection point, based off this inflection point, based off this inflection point. What I'm going to do is I'm going to base it off this inflection point. Sometimes it just makes most sense to move right. That's really the only reason I'm choosing that inflection point, and go from there. So this inflection point was originally at 0, 0. And we've already determined that it moved 2 units down, and it would move over pi over 4 units right. So in order to move right, you have to subtract. So subtract pi over 4 units right. So now we have determined the equation of our time graph. Just to kind of understand, we could even use this inflection point to determine the phase shift. Okay, you could have it y equaling tan 2. And for this part, say we said that our original inflection point moved here. Okay, well that means it would have to move it would have to move 3 pi over 4 units to the left. So we could also represent this equation as plus 3 pi over 4, because this is 3 pi over 4 units left. And they would give you the same solution. Some questions might actually ask you to give the smallest possible phase shift. Our smallest possible phase shift would either be pi over 4 units to the right or pi over 4 units left, depending on which one you want to choose. So I hope that was really helpful. If you have any questions, ask your teacher or comment down below. Thanks.